Hello, I'm Richard Maywalt, and I'm going to be telling you about the first observation of SEP electrons at MEV energies that we made with Parker Solar Probe. My co-authors are members of the EPI-Hi instrument team, EPI-Low instrument team, and other instruments on the spacecraft that contributed to this study. Here's an outline of what I'll say. The EPI-Hi telescope I will describe at first, and then we will look at the April 21st, 2019 solar event, and that's the one we're going to make measurements of. I'll tell you about how we calibrated the HET electron response and show the SEP electron spectrum that was measured in this event, and then summarize. This is the EPI-Hi instrument on Parker Solar Probe, and there are 3 telescopes. At the top, we have a high energy telescope, the blue one, which we will be using today. There is also a low energy telescope, LET-1. Both of these are double-ended. And then there's a single-ended telescope, LET-2, down near the bottom. These do look in the sunward direction, out this direction that I'm pointing with the marker, but they also look in the backward direction, and I'll show that response in a minute. So here's a diagram of the HET telescope. It's composed of a stack of silicon solid state detectors. At the entrance, these are position sensitivity detectors. They have 5 apertures, and down here, there's 5. And this one also has 5, and this has 5. So particles must trigger the first H1A and then H2A, or the opposite on the other end, and in order to get an event. And then they can't trigger any of these guard regions, which are in anti-coincidence, because we don't want to have particles going out the side or coming in from the side. This is a map of the field of view. Here's the HET telescope looking in the backward direction. In the forward direction, we can also look. Obviously, we can't look at the sun, so there's this thermal protection system that blocks the sun out, but we do see around the edges of the TPS, and so we have quite a big field of view in the forward direction. And here's LET-2, which is looking in the backward direction. And LET-1 and HET also have a backward looking response. This shows the electron energy coverage that extends from 0.5 to 10 MeV. This is the total response. This would be for a particle that goes through the first one and stops in the second detector. And then you get curves that go deeper and deeper into the stack. HET can also measure protons and heavier nuclei. The proton response extends from 10 to 50 MeV for particles that stop in the telescope. But if you pass all the way through the telescope, we can measure all the way from 50 MeV up to several hundred MeV. This is a laboratory measurement of beta source ruthenium-106. It has a spectrum that extends out to 3.5 MeV, and this is showing the response as a function of where it stops in the telescope. So range 2, range 3, range 4, range 5. Range 5 is kind of small, but it gets all the way out to 3.5 MeV, which is the maximum energy you can get from this source. This is a series of plots that NOAA makes every day to show what the sun is doing. And you can see that most of them are rather boring or blank, but there is looks like a flare that happens out here, and that's in fact the flare that we are getting our electrons from. And you can see some sunspots there. And it's basically, though, a quiet period, but we were lucky enough to get a small event during it. This plot shows what we are measuring as a function of time over a series of maybe 30 days or so. 30, yeah. In case you can see some background counts and everything. That's probably just electrons from interplanetary space, Jovian electrons or other sources. And that's just kind of a steady background. What you're looking for is when it gets bright, that means the intensity has increased. And you can see that that's happening in day 111 in these vertical segments here. Now we're going to look at the A side, and we're seeing the same stripes, of course, and these blank spots are when the spacecraft is telemetering data back to the ground, and we can't operate right then. That's why we get this slatted fence response. But it samples the large fraction of the event. And here's a histogram of the electron energies that were measured. And this is a time profile. It's going from 30, 40 days or so, and it shows a steady background. But then here at day 111, you see a spike. That's when we're seeing these electrons that we were following up there. And if we look at the B side, we also see electrons, this electron spike. When you have a solar event, electrons can whiz on by the spacecraft and then scatter in the magnetic fields, interplanetary magnetic field, and come back. And so it's ends up typically being isotropic. You get equal electron response from all directions. And here's again this histogram of the energy loss. These are examples of how we calibrated the response of the telescope. These are Geant 4 simulated electron events. This started out with a summer student who did maybe tens of thousands of simulated electrons. After that, Alan Labrador continued on and did millions of simulated electron events, so we could get very good statistics. Here's an example of a good event. It comes in through the front. It triggers several of the detectors. It may backscatter here, and then, but it stops in the telescope, so we get a good total energy measurement. And here's the second one at the bottom, which just comes in and then slows down and stops. Here's a bad event because it comes in through the front and then runs into a guard. And that way we can't tell if it was some particle that just came in through the sides and then entered. You have an ambiguous trajectory, sort of. And here's another one which came in and looks like there's a knock-on electron or something that ends up here, and then this continues on through the guard region, and so again it's vetoed, and we don't deal with those events. Here's some other simulations of event distributions where you put it in a monoenergetic beam, and then you see what the total energy you get from all of the 10 to the 7th electrons you put in. You can see that this is a log scale, and almost all of these have a very narrow response at the beam energy that was put in, and that continues all the way up to high energies. So we do get very good resolution on these electrons. There is some background at lower energies, but a typical energy spectrum in a solar event would actually come down like this, like say a power law of E⁻² or 3. And so this background was not going to disturb the spectrum of a typical solar event. Okay, for this April 21st, 2018 event, this is the energy spectrum that we get. using a response matrix to get the contributions as a function of energy. And that makes an e⁻³ spectrum, which is sort of typical of electron events. They can be e⁻² up to e⁻4 or 5. So that's a very nice measurement. And in fact, we have another measurement of that event from the EPAM telescope on ACE, which is located at L1. And it's got a similar spectrum, e⁻³.2 compared to our e⁻3. And so I think this is a nice event. It's our first one. And of course, we have measured some more recently. And some of those are even getting into publications now. But this was the first one to prove that everything worked. And it gave us confidence that we could make some good measurements. So in summary, in addition to producing an interesting helium-3 rich event on April 21st, this event also produced a good electron spectrum with similar slopes at PSP and ACE. And the GET simulations, of course, were critical to mapping out the electron response. And that's been made it possible so that we can now measure electron spectra up from 0.5 to 5 MeV and probably higher. And we look forward to a larger sample of electron solar events now that solar activity has started to pick up. Thank you.